from the Physics and Astronomy Department, Exact Science Faculty, Universidad Andrés Bello. And the title of the talk is Emergent Electromagnetism in Topological Insulator Waveguides, TM modes and polarization control as a signature of the topological magnetoelectric effect. Please.
Okay. Thank you very much, Doctor, and thank you very much for the organizers, Alberto, Luis, and Eduardo. And also, I would like to thank the Instituto de Ciencias Nucleares for the kind hospitality. So, yeah, already you heard the title of my talk. And what I want to tell you today is work based on the thesis Sebastian Filippini, a student of mine, recently defended. And it is published in this PRB paper. Also, it's based on way too long under preparation work, and most of these ideas build upon work that I've been doing with Alberto Martin and Luis Urrutia in the last couple of years in these papers. A showcase of the working group and collaborators, some undergrad students, PhD students, and this is a rather old picture, but Alberto, Luis, and myself. So I would start with giving motivations to tell you what I'm working on, and then jump to give you a general idea of this talk, and also at the very beginning give a glimpse of the results I want to arrive at. Then the core, the framework of the work is the electromagnetic response of topological insulators and magnetoelectric media, and this is a dense part of the results. And the general topic, one could say, or the title is the topological insulator waveguides, focusing on cylindrical boundary value problems, and then finding new phenomena, emergent solutions that are not allowed in usual non-magnetoelectric media, and then end with some summary and conclusions. So as a motivation, well, I always like to start with this motivation, that the fact that topological matter is a new kind of matter, it kind of lend themselves for as new toys to play with, of course to play in a serious manner, and may also shed lights on new physics. And this extract here is from Jackson's book on electrodynamics. He's talking about the issue of magnetic monopoles, and basically says that whenever you have a new window of possibilities, there is also a possibility for new physics. He's talking about, say, when you have more access to higher energies in accelerators, or he says rocks from the moon. So topological matter are not rocks from the moon, but nonetheless it's new matter, and hence we could wonder whether we can find new physics with them. I guess I don't have to convince you that we are all with the hope of indeed finding new physics. And he's talking about monopoles, and this is a figure from a famous paper by Key and collaborators, a science paper, in which they show that if you have a static electric charge in face of a planar topological insulator drawn in green down below, what you find is not only an image electric charge, but also a so-called image magnetic monopole. There is no real magnetic monopole, but the fact that this is a topological insulator induces a field that from above, from outside of this topological material, the magnetic field is as if there were one magnetic monopole there. So that's one motivation. A second motivation is to wonder whether there is a possibility to, so to say, evade a no-go theorem in usual Maxwell's electrodynamics. That is, that you cannot have transverse electromagnetic fields when you have waves confined in media with less than 2 conductors. If we go to remember our E&M course, we know that we can have transverse electromagnetic waves, for example, in the coaxial cable where you have 2 conductors, but if you have only 1 conductor and media that differ in their optical properties, you cannot have transverse electromagnetic waves. And the fact that the electromagnetic response of topological insulators with the electromagnetic field has new terms led us to wonder whether this could result in a possibility of having solutions that were otherwise forbidden. So what's the general idea? And highlighted in yellow, the results associated with each of these ideas. The first one is to describe, characterize, and also provide eventually new signatures of the topological magnetoelectric effect. And from my perspective, I will cling to the magnetoelectric effect as seen in these modified constitutive relations, meaning that if I have a topological magnetoelectric material, when I embed it in an electric field, not only will it polarize, but it will also acquire a magnetization and vice versa. And what we'll find is that due to this effect, we will see a measurable rotation of the polarization plane when light propagates in this kind of topological insulating waveguides. And this rotation is different from already reported for topological insulators, Faraday or Kerr rotation. It's a fine structure constant. Yeah, sorry. Yeah. Yeah, I forgot to mention. I will show the model briefly soon. Also, another general idea is to see if we could find these emergent electromagnetic phenomena, these transverse electromagnetic waves that are otherwise forbidden, given that now situation is a little bit different. And the answer is that we will find these solutions, and that's a very interesting result for us. And the last idea and results is that given that you have a new scenario in which you can propagate electromagnetic waves confined in media, of course, this is in a way science fiction, because nowadays to produce topological insulators samples, it's very experimentally hard issue. You in a, say, silicium substrate, you deposit the gas of bismuth celleride and you find domains of, say, 100 microns. It's very tiny, right? But we are thinking if these things were possible to do kind of waveguides or fibers with these things. And the interesting thing is that due to these transverse electromagnetic waves, what we find is that we can propagate light in these eventual topological insulator fibers, and the light propagates in there without undergoing total internal reflection. And this is very interesting, for example, in photonics. This is an image from this Nature Communications paper in which you have a sense of the scale. These in green are the, so to say, avenues for light to propagate, and you have in the center there a ring resonator, and the scales of these are 100 microns. And one of the difficulties they find is that if you want to keep miniaturizing things, you want to do very tight bends, and if you need light to go propagating with total internal reflection, there is this critical angle, because if you go beyond that, light escapes away. And what we find is that just because it propagates in this transverse manner, you don't need to undergo total internal reflection. And therefore, no matter how acute the bend is, light will not escape. So that's a glimpse on the results. So the framework is this. I think we've already seen it, describing the electromagnetic response of topological insulators with electromagnetic fields. There is a caveat for this to be a proper description of this system, is that basically the frequency of the electromagnetic fields interacting with the topological insulators has to be such that the energy associated with that field is not bigger than the typical band gaps of the topological insulators, which are of the order of 0.3 electron volts. That translates into frequencies below 70 or something terahertz, okay? So we will always remain below that frequency for this game to be valid. And the result is that the field equations get modified by terms that I've put in red here, and they all, you can see, are related to variations of this theta parameter, spatial and temporal variations. And from here on, I will only consider constant in time thetas, and also thetas that are piecewise continuous. I will consider, like in the usual E&M course, where you have one medium with one epsilon, an interface, and another medium with another epsilon. And it's isotropic and homogeneous bisectors, okay? So the effect of these terms, the effect of these terms is to produce contributions to the discontinuity of the components of the electric and magnetic fields. This term produces a discontinuity, additional term to a discontinuity in the electric normal component of the electric field. Sigma here is the interface between two media. And this term produces a contribution to the continuity of the parallel magnetic field to the interface. So the idea is that given that these terms modify the boundary conditions, the question is to focus on situations that are highly sensitive to boundary conditions. And one of the situations in which boundary conditions are very important is wave propagation in confined media. So this is a picture of the generic setup that I will be discussing. The idea is that we have, say, an incoming electromagnetic wave with a certain polarization. It goes through a medium and emerges probably with a different polarization. The amplitudes of the fields get modified and so on. And in here I'm depicting coaxial cylindrical surfaces and they may differ in their optical parameters epsilon, mu, and theta. And the question is, well, what are the properties of the outgoing electromagnetic field?
Sorry, can I ask you a question about the previous example? These are the equations of axion electrodynamics.
Right, with a constant axion.
Here it's not constant because it's a function of time and position.
Not from our perspective.
There it is.
Yeah, these are the general equations. So
otherwise you will reduce to the ordinary equations if you said theta to be constant. Oh, at the boundary.
at the boundary it will change. So you will have.
So you will assume, so the bulk essentially is constant.
Right.
And you assume that there's a change, say from pi to 0 or something.
Right. Mm-hmm. Yeah. These were the general equations, and I'm.
You complain that there is no equation of motion for theta.
No, there is no question for it at all. Yeah. Mm-hmm. By the way, these cylindrical geometries is what I will be showing here, but also with Alberto and Luis, we're working on planar situations similar to this, propagating in slabs. Mm-hmm. So, it turns out that we do find transverse electromagnetic fields. I'm not showing the details of the calculation, but it's something that it's relatively simple and can be done. Here I'm showing a general geometry, and what is interesting is that in order to have these transverse electromagnetic waves, the dispersion relation, the general one, Eduardo, you were asking constant theta, the general one is this. The dispersion relation gets modified, but if theta is constant in time and does not vary in the direction of propagation, in my coordinate set is the direction of propagation, then both these terms are 0, and you have the dispersion relation, the free dispersion relation in an epsilon mu medium. And what's interesting is that the electric field, these blue arrows, these are not like the k vector, the propagation direction, but rather the polarization of the wave. They undergo, the electric field undergoes a rotation. And this is the amount by which the polarization rotates from one medium to the other. What we call anti-parallel and parallel configurations are related to the directions of the gradient of theta. These two arrows are anti-parallel, these two are parallel, and what happens is on one side of one interface to the other is related by this equation, and the theta parameter enters here. Also the optical values of the media. Theta tilde is the difference in theta between one medium and the adjacent one, okay? And here, well, sorry, you can't see very well the amounts of their rotation, but these rotations are sizable. I will show in a few slides the angles of these rotations.
What is the difference between 3 pi and 5 pi? Isn't this a modular quantity, 0 pi?
It is, but as far as I understand, a given topological insulator can be in different states with different values of pi's. The details as to how you achieve that, I don't know, but that's, I guess, a more experimental question. But in several papers, you can see, for example, say, take bismuth selenide, and it can have 0, pi, 3 pi, and so on.
So similarly, the gradient of theta at the boundary rotates as you go around because the boundary is curved.
Right.
Does that matter?
Not in our geometry.
Well, if it is flat, it doesn't, but in the circular geometry, it's pointing one way or pointing the other way.
Right.
So does that have an effect?
Well, the effect is that this all, so we are using a cylindrical geometry and also, so to say, a cylindrical symmetry for the gradient of theta. And the effect it has for us is that it produces a rotation that I will show in a minute. The pattern of the rotation is sensitive to the fact that, right. And it's different from Kerr and Faraday's rotation because usual rotations that have been measured for topological insulators are reliant on the fact that you have a magnetic field in the direction of a propagation. And given that this is transverse, this situation is completely different. So in red here, I have shown the total electric fields. Index I is in each media, this radial media, and it has, and I will study first the situation in which you have an external electromagnetic wave, say impinging on a cylindrical geometry. So E0 is the external electromagnetic wave, and E theta is the vectorial component additional due to the theta parameter, and the structure of the field is not so relevant. Let's focus on the results. And here I'm plotting the degree of rotation in millirads, and I'm plotting it here as a function of the permittivity to show that this is not an artifact, and it's all due to that you have say a trivial material in terms of the permittivity. And this diamond, cross, and asterisk represent some well-reported materials, bismuth selenide with a permittivity of 16, and thallium bismuth selenide also with theta of 11 pi and epsilon equals to 4. And these all lie in these plots. And you can see, therefore, that the rotation is something that it's, on the one hand, theta triggered, and also it can happen for different values of permittivities of materials. So regarding your question, Eduardo, what's the role of having this gradient going perpendicular to the radial direction? In these plots, you have to imagine that the topological insulator fiber is coming outside of the plane. And in the different plots A, B, C, D, the difference is the value in theta. This one, 27 pi, is maybe fantastically large, but 11 pi is reasonable for some known topological materials. And what we are plotting here is the averaged component of the pointing vector, given the transversalities all along the perpendicular direction, the z direction, relative to the pointing vector as if there were no topological insulator, or, so to say, as if all the media were topologically trivial. So the white color is no variation at all. Red increment and dark black and blue is decrement. And we see this anisotropic pattern of the electromagnetic field or the power. And this can be explained due to a topological induced currents that come from the equations, the Maxwell's equations and the boundary term. One can read from them a sigma theta, is maybe too little there, but it's related to the normal component of the magnetic field to the interface. And there's also a current, I'm not writing it here. And here I'm showing you like a recursive argument, no, not recursive, but iterative argument. Imagine that you have the wave propagating, and at the very first instance, you have a magnetic field in the horizontal direction. This magnetic field in this direction, in here, it will deposit charges, and over here, with the opposite sign, there is a minus there, so one has to take care with that. So at the very beginning, we have a situation where you have topologically induced electric charge in this distribution. This then generates an electric field, which comes along with a magnetic field pointing downwards, and this will deposit charge here, and so on. And it turns out that the total electromagnetic field, one can, so to say, do this infinite sum of this whole procedure that I described, and the total electric field doing so by computing these fields from these deposited induced charges, and it's exactly the results of the electric fields I had shown before. This is a similar representation of the amplitude of the electric field only due to theta. This basically is telling us the same physics, so I will skip it. And this is so we did this analysis for several polarizations, and what I want to show you here is first for a linear polarization. This is our linear polarization. We took the electric field in the y component, which is the vertical axis here. Z is coming out of the plane. And the first line is what happens when you have an electromagnetic wave with theta equals to 0. And here with this ridiculously large value, but just to show qualitatively the results. And in the first case, this is an animation that is showing the field in different time stages, time lapses. Unfortunately, I think it's running too fast, but in the first row, we see black, red, white, and it's because the electric field is going up and down from the maximum to 0 to the minimum, right? From red to white to black. That's what we're seeing, is the electric field flipping up and down. And the temporal effect of this is that it sums up to having nothing but the same as the electric field, as if the topological insulator were not there. What happens when one has the topological insulator? So I apologize, maybe it's hard to grasp it because it's going too fast, but maybe I can describe it. I can go manually. I did my poorest man version of this. In case it didn't work, I will go slower. So first, you have a, oh, sorry, there. So for example, you have nothing here, then this polarization occurs, and then it decreases, and then it occurs again, and so on. And the temporal average of this is that you have like a static anisotropic distribution of the electric field intensity. One may wonder what happens for a circular polarization. I will not show the first animation because it's also trivial. Now the electric field is twisting, right, because it's a circular polarization. And down below here, what's interesting is that, again, Eduardo was asking the role of the gradient of theta going parallel to the radial direction. But now, as the electromagnetic wave is twisting, it turns out that, so to say, the induced charges get fixed with the component of the magnetic field. So in this animation, what one has is that this anisotropic pattern goes like a fan. It goes spinning. And here, I guess it will go too fast also. These are time lapses. Because we are, for doing this, we are evaluating our equations in the oscillatory time dependence. And what's interesting is that in the temporal average of the spatial distribution, we have inside a isotropic distribution. Outside is also, but on the rim of the surface, we have a contribution that it's slightly above the theta equals 0 contribution. And this is because what we can see here, the subindex 2 is the media outside. And you see there is a isotropic dependence. L here is the radial coordinate over the radius of the topological insulator. So this is isotropic, this is anisotropic. But the anisotropic part, on the temporal average, it washes away. And all that remains is the isotropic part, but it has a very faint contribution as you go away from the interface, because it goes like 1 over r to the 4th power. So this is what we're seeing in this very faint yellow color. We did a similar analysis for the case of elliptical, right elliptical polarization or left. And the situation is that basically what one finds is a superposition of those two phenomena with circular and linear polarization. Sorry, I don't know, how am I doing in time? 10 minutes? 12 minutes, okay, thank you very much. So if the previous, okay, let me say something. What I show you is all done, the results are predicated on analytical calculations. It's science fiction in terms of the difficulty of elaborating things like optical fibers of topological insulators, but the results are analytic. If that was science fiction, this is even more science fiction, because now we're entertaining the idea of having several spaghettis of these topological insulators disposed in these crazy geometries, possibly with different radii and with possibly also different values of the theta parameter for each of these cylinders. But what's interesting is that one can see that if you dispose them at will for whatever purposes you may have, you can enhance at the center of this configuration in a more than twofold time the power that you're transmitting in that region. Or maybe here you have like this ring-like configuration in which you have a gain above the normal configuration. Normal, I mean with with theta equals 0. So that was the first example of these results, basically one theta interface. Now, I'm showing you a second result in which we will have two interfaces. And more specifically, the center of this will be vacuum, or topologically trivial, say. The outside, also topologically trivial, and the inside will be a regular topological insulator. So this is like a topologically insulating sheath. And again, we found that we could host transverse electromagnetic waves inside this fiber. The total electric field has a component of the external electromagnetic wave propagating parallel to the spaghetti-like configuration, but with an additional contribution that it's also proportional to theta. And these electric fields, E1, E2, and E3, are the fields inside, in the TI, and outside, respectively. And they all have a special distribution that can be seen more easily in terms of the pointings. Here I've introduced a parameter, chi. Where is it? Here. It's in all these expressions. Chi is a kind of aspect ratio of this fiber, the quotient between the internal and the external radii. And so these are also coming from the analytical solutions that we find. Again, we are plotting the pointing, the total pointing relative to the pointing as if all the media were topologically trivial. White color being nothing compared to theta equals 0. Red is a gain, blue is a loss. And what are we seeing here? Again, we see this anisotropic distribution of the electric field intensity. And what's the difference between the right and the left panels? The difference is that in here, we chose an arbitrary aspect ratio, quotient of the radii. And in here, we chose at will a configuration in which the so to say, the electromagnetic field gets much more confined inside the topological insulating sheath. From this, we can compute the powers transmitted in each media. The power inside is trivial because it's as if nothing were there. The power inside the TI and outside. So here we have P1 is the power inside P1 is the power inside in vacuum, and P2 is the power in the TI. And what we can see is that for given aspect ratios, we can optimize the power that we are transmitting. In here, for example, P2, this is the power transmitted in the PI. And we can see that for given parameters of the aspect ratio, this power, so these different curves represent different values of thetas. And for example, if you focus on the green one, this is all constant theta, but there is one parameter for which the power inside the TI gets maximized. And similarly, one can play with the aspect ratio in order to minimize the power that you are transmitting in vacuum inside. So you can play with this in a way to maximize the power output inside the TI. This is also showing similar physics for the same configurations, and I'm showing here only the component of the electric field due to theta. And the conclusion is that the electric field can be controlled and confined within the fiber if one adjusts this aspect ratio parameter. And also the fact that there is a polarization rotation tells us, I mean polarization rotation with respect to the background field, tells us that this confinement can be measured because you can disentangle it. Because since it has a different polarization, you can tell it apart from the normal component of the electric field. And so I've been talking a lot these transverse electromagnetic fields solutions, and with Alberto and Luis several years ago in this paper, we first realized that in fact maybe these transverse electromagnetic fields were possible because in the context of theta electrodynamics, as we comment here, so to say, in theta electrodynamics, one can circumvent Earnshaw's theorem, that is precisely what precludes these kinds of solutions. In there we said we are not claiming that we have proven the existence of such solutions, but here we are showing concrete solutions and examples of this. This is another example of a similar situation. We have only one conducting surface and only a theta interface. And here it is interesting because the condition to be able to host transverse electromagnetic solutions within this waveguide, this scenario would also be forbidden without topological magnetoelectric media, because this is only one conductor. We cannot have transverse electromagnetic wave in a hollow pipe, conducting pipe. And if you do this with different epsilons on each of these interfaces media, you also won't be able to host transverse electromagnetic waves. The interesting thing is that in order to be able to have this solution, we have a condition. There is a lot of computation here, I'm not showing them, but the condition is that we must satisfy this relation, and it relates the geometry. This new parameter is a parameter related to the separation constant in the solution of the electromagnetics equation. Yeah? Because our equations, although they are time depending, the vectorial part is as if they were static equations. It's the same deal as in ordinary electromagnetics. So this is the new parameter, and this condition to be satisfied, we must have that the theta is purely imaginary. Okay, so this is like triply science fiction because it's hard to build one of these things, and theta to be purely imaginary, that's arguable. I'm not claiming this is realistic, but also there have been some works recently by Ahn, A-H-N, I don't know how you pronounce that name, in which they present results to extend the axion electrodynamics to a wider range of topological values for the topological material, and they conceive the fact that the theta parameter depends on the frequency, and in that frequency dependence, it may acquire real components vanishing and imaginary components non-zero. To satisfy this condition, again, the electric fields acquire a weird shape that depend on the separation constant, and here I am showing explicit solutions for one of these values. And below here, we are plotting what the solutions would be like for nu equals 1, 2, 3, and 4. And what we find is that the electromagnetic field inside, there is a conductor here and the interface between two theta media. What produces is that the electromagnetic field intensifies in these regions, and this resembled to me as the shower nozzle selector. Okay, science fiction, purely imaginary theta to construct these things, but okay, it would, by adjusting theta, you could funnel within this pipe, you could funnel light even in finer geometry, so to say, because you could produce these patterns which are totally different from these ones. So to summarize, I've shown that these exact transverse electromagnetic waves are possible. We showed a concrete realization of what we thought with Alberto and Luis years ago. And these solutions, I emphasize, they are forbidden in topologically trivial materials. They are, I call them, emergent topological transverse electromagnetic waves, and are solely due to the properties of the waveguide, and yes, of the particular geometry and boundary conditions that we choose. They provide an observable signature of the topological magnetoelectric effect, and also thinking with the case of two interfaces, this may be of certain interest to people doing photonics for the reasons I explained previously. The fact that you have a transverse wave allows you, for example, to bend a fiber in a very acute angle, and you won't have leakage of the electromagnetic field because it doesn't need to comply with the incidence angle to be below the critical angle. So that's it. Thank you very much.
There are questions?
It's a bit of a comment and maybe even more science fiction. This is kind of a practical problem for information storage, okay? And usually to kind of turn a spin, you want to have a solenoid, and so that creates a lot of heat. And so a solution to switch these spins is to have materials that have intrinsic electric and magnetic dipoles. And so then you have a coupling like the one you show, with the alpha. Actually, the variable is the same. And those things are electromagnetic multiferroics. And so this is, a very applied kind of thing. So I was wondering, and this is sort of the science fiction kind of the comment or question. So it seems here that you could, use an electric field, and then at the interface of these, cylindrical cavities, you could place maybe some magnetic materials where you know that the magnetic component is going to be large, and maybe you can have the same effect. But again, it's kind of a comment, and yeah.
Yeah, thanks for the first comment, and regarding your second comment and question, there's this whole deal as to how to produce to make a material become a topological insulator, and you may deposit say a layer of high magnetic field, but that would be, so to say, localized at the interface and wouldn't interfere with what happens above it. I don't know if that sort of replies or complements your words.
There are questions? No? Well, I have a question. You have conditions about this topological insulator, which or nothing? It's only.
You mean if there is a condition?
Yes, when you change the sector that is topological or not, the topological sector has some conditions or not?
Well, I would say that there is certainly an experimental constraint, but that I'm not knowledgeable of, because how to produce a cylindrical topological insulator with uniform topological parameter, I am sure that is a tremendous challenge. That's a constraint. From our perspective, I am taking that for granted, so that's why I'm saying this is like science fiction, but our real constraint or condition is that the energy of the electromagnetic wave that's interacting with your topological insulator needs to be below the typical band gaps of the topological insulators. If you comply with that, then the action electrodynamics with theta constant by sectors and in time, that's legitimate.
Okay.
If there are more conditions or constraints, I'm not aware of, but I think it's only that.
Thank you. Well, we thank again the speaker. Let me see.
Por favor. Sí. Sí, muchas gracias. ¿Ahí? Es la que dice, no, esta. Gracias.
Okay, then the next talk is imparted by Arturo Camacho Guardián del Instituto de Física del UNAM, and the name of the talk is Intercavity Polaritons, Flat Bands, and Topological Phases.
Okay, thank you very much. So I would like to start by thanking Alberto, Professor Urrutia, and Eduardo for the invitation, and also it has been a very nice workshop where I've been learning a lot. I have to admit that what I'm talking about slightly deviates from the scope of the workshop, and I have to apologize for two things. So the first one is that I think that some of the animations that I have prepared got lost when I made it to PDF. And the other one is I'm taking the opportunity to, because it's a workshop, to describe in some detail some concepts that perhaps are trivial for some of you, but I still want to be as self-contained as possible. Okay. So the scope of the talk is quantum Fritz-like, and I'm particularly going to talk about a concept that I'm going to define later, that it's polaritons, and it's a nice concept that appears in several fields in physics, from AMO, like atomic and molecular, and optic physics, condensed matter, and the main part of the talk is going to be about polaritons in some chemical physics. And something I think that it's really nice is that one can have some building blocks that are very simple, to some extent, and still, even though they are very simple, there are very nice physics and non-trivial physics, and from those building blocks we can go and create some complex states of light and matter, like many-body states or strongly correlated states. And something that is also very nice is that the field theory approaches that we use span from what we heard with Rosario's talk, that was talking about nano-Kelvin experiments. The condensed matter work more or less in the Kelvin regime, so it's low temperature, but it's not ultra cold. And some room temperature experiments that are performed at the Institute of Physics. So let me start with AMO, atomic and molecular physics. And I'm going to talk about three-level physics, which is going to start looking very simple, but then we can grow from there. So I'm going to introduce two concepts, bright light and dark light. This one seems like a bit of even pleonasm, because light is always bright, and the other one looks like a contradiction, right? But let me just go and explain what do I mean. So what defines a medium, whether it's opaque or transparent, well, it's how it responds to light. So if we come and shine a photon, right, then for instance, if the internal structure of the atoms has a two-level kind of nature, we have the ground state where all of the atoms initially are sitting, and then we come with a photon, right, that matches the energy of this transition, then the photon an atom can absorb the photon, and then by a spontaneous emission, right, the photon, right, is going to go away, and the emitted photon does not necessarily goes in the direction of the initial pulse, right? That means that if we have a pulse that is propagated in the medium, it starts to be attenuated, right? Because like this spontaneous emission is happening, and then if an observer, right, places like it's here, like not in the direction of the initial propagation of the light, it starts to see like light coming from this process of spontaneous emission. And then we say that the medium is opaque, right? Because it's absorbing the photon, that are afterwards being spontaneously emitted, right? So, but like we can assist like the propagation of the photon with coupling this excited state to a metastable state C, right? And then when light propagates in the medium, right, then it can propagate in a form of a superposition of a photon state and a metastable state C. And if the metastable state C is long-lived, right, for all practical means, this, what we call polariton, that is this linear superposition of a photon and a matter excitation, is long-lived, right? So the medium becomes transparent, and we call this electromagnetically induced transparency, because we are inducing transparency by coupling the excited state C to the C state. And when we do this, and the E state is no longer part of the P, or of the polariton state that we call dark state, then it has deactivated the spontaneous emission mechanism. Then we say that this is a dark state or dark light because an observer that is not sitting here, right, never sees light, right? And then we say that this induced transparency, and we call this a dark state, right? And one of the consequences of this mixing of photon and matter is that the group velocity of the light can be reduced dramatically. And we call this slow light. And then I'm going to tell you a bit more about this. So the mathematics is very simple, because like it's a three-level system. Then we can represent this physics by simple like a 3 × 3 matrix, right? Which looks like this, right? So we have the energy of the photon, the energy of the excited state. We include the fact that the E state is short-lived, so it has some damping. Then we have the coupling of the photon state to the E state that is amplified by the number of bosons or atoms sitting in the B state. And then we have the metastable state C that couples to the E state via this classical field. Then a particular case is when the energy of the photon state matches the energy of this dressed C state, and we call this on resonance, right? When the energy of the photon and the C state matches, then one of the eigenstates of this matrix has this particular form, right? And has no E component, right? Which means that the E state is not part of this form of light. So that's why we call it a dark state or a polariton, dark state polariton. So then the polariton is just the superposition of the C state and the gamma state, right? And that's what I was telling you. A dark state polariton emerge. The degree of mixing, right, are these cosines and sines, right? And like the slow light tells us that the group velocity is proportional to this cosine of theta, which can be made like ridiculously small, which means that light can be slowed like very dramatically, and the medium becomes transparent, right? So how slow? Like the first experiment in 1999 by the group of Lin and Hao, they managed to reduce the propagation of light up to 17 meters per second. Just to give you a rough idea, like the speed of the cycles that you can see here, like in the mornings, are more or less 70 meters, like 40 kilometers per hour. And in more recent experiments, they can actually stop light for some time and then make it propagate again. So like it can be very dramatic. So I think that's like a very nice effects of optics, right? And this is like the building block I was telling you, and people has investigated what can we do with this. And for instance, they have managed to create, when light and matter mixed, light can do things that usually don't do in vacuum, like for instance, create molecules or these photon bound states, or what we have done, like quite not so recent, like 5 years ago, like now it looks like very, very far away, is for instance, like create superfluid flow of polaritons in a Bose-Einstein condensate, or to look at strong photon-photon interactions. Now let me just move quickly to condensed matter, right? And also tell you about like this very simple, in principle, three energy level schemes, right? So, and then like here I'm going to talk about some very simple physics. Like we all know that in a semiconductor we have a field valence bands, and then a gap, and then the conduction band, and then if we shine, if we excite an electron from the valence to the conduction band, it can create a pair of electron and hole that we can regard as a bound state, which is the exciton, right? The exciton is the bound state between this hole, right, and this electron that are attracted via Coulomb interactions, right? And this bound state, of course, is delocalized in momentum space, which means that it's localized in real space. And it really looks like a nitrogen molecule, right? So, and it's characterized by a excitonic Bohr radius. And for all practical means, like it usually is regarded as a point boson, right? This composite object is regarded as a single object that we call the exciton, that it's a boson. Then the polariton, well, right, it's a dress photon, and how we dress the photon in this context, well, what we do is that then we can create the exciton by shining light. So we send a photon, and then what we do is we place the semiconductor inside a microcavity such that this process of absorption and emission of light by creating this exciton, which decays again and creates the photon, repeated hundreds of thousands of times inside of the cavity. Then when this happens, the exciton and the polariton mixed and form a hybrid state that we call, again, the polariton, which has this very similar form of the photon state and the exciton state, right? And in conventional cavities, like we can regard the system as a two-level system, right? Because we have like just two states, the exciton, the photon, that couple via like a conventional like matter coupling. But in this heterostructure, van der Waals heterostructures, we can do some layer stacking, which means that like with advance of graphene, like people have investigated other graphene-like structures with different electronic properties, like that range from metallic, semiconductors, or insulating. And when they stack the layers, and the electronic properties change, right? And this is like the Lego picture that like it's more fun, right, to have more than a piece of Lego, right, than just one, right? So like you can build more interesting stuff, and in the context of physics, right, and in particular electronic physics, like besides these somehow boring states, we can have many body physics that are superconductors, topological phases, Wigner crystals, mode insulators, right? But we can also have exciton phases in semiconductors, right? So then the idea is that we are going to have a bilayer of two semiconducting layers, and we are going to have two kinds of excitons. One is an intralayer exciton, where the hole and the electron live in the same layer. And this exciton is especially direct, so like both components are in the same layer, and it couples strongly to light, right? One of the disadvantages is that the exciton interaction in these materials are usually very weak, right? Because like there are like point objects that only interact when they are on top of each other. But what we can do is to create an interlayer exciton where the electron and the hole are in different layers, right? Then it's especially indirect. It couples weakly to light, right? But because it has a permanent dipole moment, then it features strong exciton-exciton interactions. And via the hybridization of the intralayer and the interlayer exciton with electron or hole tunneling from one layer to the other one, then we can have hybridization of these two states, and then we can get like the two features that we want, right? Strong like matter coupling and strong exciton-exciton interactions. And then this is again like three-level physics, right? That has been realized in the group of Atachi Mamogu like almost 7 years ago. But like what is interesting is that the energy scheme looks exactly as the one we were referring in the context of atomic physics. Then something that is also very interesting in this system is that if we start twisting the layers, so we see that we have here like the stacking of two layers, the red one and the blue one, and they have a small lattice constant, but we see the emergence of a larger pattern that we call the Moire superlattice. Then the excitons, when they are embedded in this configuration, initially they have this parabolic dispersion, but what they tend to do is they tend to localize to these Moire sites. Then the quadratic dispersions of essentially free excitons in the two layers become flat, right? They become flat because they start to move in this, they are restricted to live in the sites that like you can see here. And this is an effect that was demonstrated in 2019, right, in the group of Vladimir Falco in Manchester, right? And then, like, one can effectively describe the excitons with a Bose-Hubbard model, right? Where we have the tunneling of the excitons that are restricted to the sites, and they can just jump from one side to the other one. They have this exciton-exciton interaction that is strong because they have a permanent dipole moment, and the energy that costs to put an exciton in a given site, right? Then, in the limit of strong interactions that like are more stronger than the Hoping ratio, what it forms is a dipole ladder, right? So like the energy spectrum of the Hubbard model can be obtained analytically very simple. And then we observe a phenomena that it's also very intuitive, right? So like if we shine light such that the energy of a photon matches the energy of a single exciton, then what we promote is the occupation of this state, right? Then if we come with an energy such that the energy of two incoming photons matches the energy of two interacting excitons, then what we do is we promote the occupation of this like double occupation state, right? Then we can do like the same with three photons, and then we can arrive to a very simple energy condition that simple reads that if we shine with energy such that the energy of n non-interacting photons that we are injecting into the system matches the energy of n strongly interacting excitons, then we are promoting this multiphoton resonance. And then, like the parameters that describe this, like this driving of injecting photons is how strong are we driving photons into the system, and the detuning, that is simply the difference between the energy of the photons that are injected into the system and the energy of the exciton. Then the occupation number of a given site looks like this. So then we see this kind of lobular pattern that follows some discrete pattern. This is a work that we did in 2022 with Nigel Cooper when I was a postdoc there. And a couple of months later, there was this demonstration of the dipole ladders in this Moiré lattice, where they were demonstrating exactly this rule that I'm telling you of how the emission and the absorption depends on the energy spectrum of the Hobart model, essentially. So then now let me just change the topic again, because this is the main part of the talk, and it's about polaritons in organic semiconductors. So the idea, and it's what I'm going to say, it's going to sound like very trivial, right? So like the idea is to have a nanocavity where we placed inside some organic molecules that host an exciton. So the idea is that we have the molecules and the absorption, or like this is the like essentially the index of refraction, right? Then we see that this particular molecule hosts an exciton, and then we can regard this system, right, as a two-level system, right, where we have a mode of the photon that couples to the exciton, and the hybridization creates these two polariton states. Of course, that if we want to the photon and the exciton to hybridize, we have to put the molecules inside the cavity, right? Because like they have to specially localize, to specially overlap to hybridize, right? To couple, right? So we would like to have the electromagnetic field that is this one to overlap with the molecules. Otherwise, it sounds actually stupid to put the molecules outside the cavity, right? Somewhere else. So that's what I said. That is really obvious, right? But like the question is it really obvious, right? Is it really such that the only way to create a polariton is that the photon and the excitons overlap? So, or is it possible to create a polariton where the photon and the exciton are spatially segregated? And this is, like the answer is yes, it is possible to do that. And the answer has to be like a three-level system. That's what I've been talking here, right? So the idea is instead of having like this two-level configuration, to add a third level, and then what is this third level? An empty cavity. So the idea is that we are going to have an empty cavity that has no active medium, so it has no excitons. Then we have our cavity here that it's filled with molecules that have this exciton. Then, like what we can have, right? Well, actually, what we have is that we have like these two cavities, and the photons are injected from the left cavity, and the photons, once are here, they can tunnel because they are separated by a very thin mirror. So then there is a coupling from the left cavity photons to the right cavity photons, right? So then this tunneling, and then our Hamiltonian is again very simple. It's a 3 times 3 matrix where you have the energy of the left cavity photons, the energy of the right cavity photons. Like then we have the coupling between them that are via this tunneling, and then we have the like matter coupling that is local, right? So like the exciton and the right cavity photons, they couple because they're actually like in the same place, right? At resonance condition, then we can guess what is going to happen, because we are going to obtain an eigenstate of this Hamiltonian that is a linear superposition of the left cavity photon and the exciton, right? So then we have an average state of light and matter that their components live in are separated in space, right? Which we believe it's kind of cool, right? Because it was like the first time that it was made such a polariton, right? So, such a form of light where the hybridization is non-local, right? And then some ideas to do some quantum tomography, right? Where we can prove like the matter and the photon part of the excitons without actually disturbing like one of the other. Like we can do local measurements that is impossible in a conventional single cavities, right? And what we actually gain, besides this nice polariton, intercavity polariton that is especially segregated, is that we obtain a polariton that is a heavy mass polariton. So like the dispersion of the polaritons usually is quadratic, and when we have this configuration, we can control the mass of the polariton. And then we did this in the experiment. So this is an experiment that we did at the Institute of Physics, and what we show is as a function of the detuning of the left cavity photons and the exciton, and then this is when it's far detuned, so like the energy of the left cavity photon is far away from the energy of the exciton, and then we have here like the 3 polariton branches, and then this is the polariton branch we have to focus. And then when we are exactly at resonance, then we see that this polariton branch becomes essentially flat, right? And this is like the theory that is supporting this reflectance spectrum, which what we are showing here is like something that is called the spectral function. And just let me just mention how we know that those are intercavity polaritons that have no component of the right cavity photon is by looking at the quasi-particle residue or the Hopper coefficients of these 3 polariton branches. So what we have to look is that we have this middle polariton branch, so like this one, and this one, and what we plot here, right, is for like this is for A, this is for B, and this is for C, right? Then we plot like the 3 components of the polariton branches in terms of the birth state. So that means that we have the overlap between the middle polariton, this branch, and the left photon, right? The overlap between the middle polariton and the right cavity photon that we would like to show that it vanishes, and then the overlap between the middle polariton state and the exciton state. And when we are far away from resonance, then we can see that here at normal incidence, like the right cavity component is non-zero, right? So it's non-zero, it's here, which means that the polariton we are creating is an average state of the 3 birth states, right? So like it's a polariton that has composition of the left cavity photon, right cavity photon, and exciton. And as we move towards a resonance condition, then we start seeing that the component of the right cavity photon, that is this blue curve, that it doesn't look like very nice here, start to vanish. Exactly on resonance here, right? It vanishes exactly. And something that is very interesting is that it vanishes not only at normal incidence, where we can prove that it has to vanish exactly, but it vanishes over some angular regime, right? And we can also prove like that we are seeing a pure intercavity polariton that is spatially segregated via some photoluminescence measurements. So what we do is that we first inject photons from the left cavity when we are far away from resonance. And then we see emission from the middle polariton and the lower polariton. But when we are exactly on resonance, if we shine light to the left cavity, then because this middle polariton is completely decoupled to the right cavity, right, then it has no mechanism to actually couple to light. And then it cannot emit, right? And then this is the dark side polariton. And then this first part of the experiment was performed by our experimentalism, in particular the group of Hugo Lara, Giuseppe, and Cesar. And this is like our postdocs, students. And it was published here, right? And we were actually very happy because this was a 100% homemade experiment. And now, we are looking at a way to protect the intercavity polaritons over this angular regime that I was telling you. So the idea is that we fix the resonance condition, so which means that at normal incidence, we have an intercavity polariton, right? So here. And then what we are going to tune is the energy of the right cavity photon. And then if it's detuned to positive values, then what we have is that the intercavity polariton breaks quite easily, right? So it's here where it breaks, where it has having right component. But when we start decreasing the tuning, then we see that the angular regime for which the intercavity polariton exists, it expands, and it can become very, very large. So we can have an intercavity polariton that spans essentially over a very large angular regime. And well, I mean, this is something that I wanted just to connect, to have at least one slide that connects to the title of the workshop. And this is something that we would like to do. So we would like to have a stack of cavities and to start doing some topological phases with polaritons. This is actually a work that we did, but experimentally it's kind of hard to make this this proposal, right? And then we have some ideas that to create some to have strong polariton interactions that can be controlled remotely, to do quantum tomography locally for quantum information. We would like to see if we can create a Bose-Einstein condensate of polaritons to have some anomalous dispersion, like in some particular cases we can have polaritons with negative mass, and to study the dynamical formation of the polaritons. So then, I would like to conclude by saying that the building blocks that may perhaps look very simple, but still we can have very interesting physics, such as the production of slow light, that is I would say a very amazing phenomena, hybrid polaritons in condensed matter, or these intercavity polaritons that are the building blocks for more complex many-body phases, such as bound state of photons or quantum memories, or these dipolaritons or dipolar ladders, or to create some strongly correlated polariton states. And this is an open question that we are doing in the experiment. Well, we don't, but the experimentalists. So with that, I would like to conclude, saying that it also spans a wide regime of energies, right, which makes it even more appealing, right? So yeah, and then I would like to finishing by acknowledging the grants that are supporting these studies, and also the organizers of this very nice workshop.
There are questions, comments?
So I have a question on the cavity part.
Mm-hmm.
How does those molecules, how are the molecules held? within
There
the
is a
cavity?
polymer in between, so it's not.
There is a polymer?
Yes.
Oh, okay. Okay, thank you.
Another question? If not, we thank the speaker again.
bolsillo, en el cinturón, donde guste. En el bolsillo. Sí, sí. ¿En el bolsillo? Sí, o en el cinturón, donde sea. Ahí está. Y en el suéter aquí. Aquí justo en medio. Así está.
Para
Yo
cambiar.
le subo para abajo.
Así.
Ese es el láser.
Okay.
El láser está abajo.
Okay. Well, do you hear me? Is it okay or not?
Sorry,
Maybe I can.
let me introduce you. Pavel Castro Villarreal from the Facultad de Ciencias en Física y Matemáticas, Universidad Autónoma de Chiapas. He is going to talk towards topological states in curved 2D materials. Please.
Well, first of all, I would like to thank to the organized committee of this wonderful workshop on topological quantum matter. And also I would like to thank to all the workers here in the Institute of Nuclear Science for all that they do to be possible this workshop. Well, as it was mentioned, the topic is about some working, well, I will divide the outline of the talk will be divided in two sections. One, which I call graphene shapes from quantum elasticity, is a work that I have been working recently, and last year was published, and so I would like to talk most of the time about this work. And the other is some preliminary work that I have been done in order to understand topological states in curved material. In some sense, I would like to say that the first section, I don't know if it's that the correct name, but it's about classical topology, and the other one is like a quantum topology, in the sense that the topology in the first case is just associated to the structure of the material, but the topology in the second case has to do with the quantum information of the material. Well, so let us start with this one. The first thing that I would like to mention here is that since the synthesis of graphene, it is known that the graphene is not flat. It typically appears with nanoscale corrugations. For instance, in this paper, which is something like 15 years ago, through a scanning electron micrograph, they show that there is a very strongly crumpled graphene sheet. And also there is another article in 2010 using a scanning transmission microscopy showing also that they can form using graphene nanobubbles. So the reason that graphene can have these properties, that you can consider graphene like a sheet, and this sheet can be bended or can be curved. So this allows us to ask what are how the curvature of the graphene sheet is influenced in the electronic degrees of freedom of the graphene sheet. And actually, more or less, I would say 8 years ago, in 2017, we did a study of low energy regime with the Dirac equation in curved space-time, and we able to show a very nice formula that I will put here. Is basically a relation for the pseudomagnetic field when graphene is curved. Yes? No? Maybe here? Okay. Is the pseudomagnetic field that is produced because of the bending of the graphene, which is something like h bar 4 over electron charge and the curvature. And this curvature is the Ricci curvature. And actually, this formula appears not just in one valley, also appear in the other valley, but with the negative sign. So for instance, this is one of the effects that appear in the graphene sheet when you have curvature. Also, it is known also that from even before the groundbreaking of graphene, of the synthesis of graphene, that the curvature has a, I mean, if we see the graphene sheet as a continuum media that has some curvature property associated, we can say that the curvature is a macroscopic manifestation of the existence of topological defects. Basically, the topological defects appear necessary in order to balance what I call the classical topology, because, I mean, for instance, a plane of graphene has Euler characteristic equal to 0, but if I can, for instance, in this catenoidal graphene, we need to put some heptagonal rings in order that this hypothetical material has the right topology, I mean, has the right Euler characteristic topology associated to the topology of the catenoidal surface. So this is what I call I would say, classical topology. So although it is known, but I will just mention that just in the end of the talk, that these rings, heptagonal rings, can be characterized in a low energy description using the Dirac equation in Curie space, introducing a non-abelian gauge field. So for instance here, if we want to, we can cut this triangle of the graphene, and we can have a deficit angle, for instance, in here. And we are able to put this declination, and this is going to be a topological defect, which is characterized by this heptagonal ring. Okay, and also, since the synthesis of graphene, in this very famous paper by André Geim and Novolesov, they were thinking that the possibility that the graphene can be cut in some shapes such that this can be considered as a model of all graphitic forms. For instance, we can take pieces of flat and construct graphite, or roll up in order to find the carbon nanotube, and also fold up in order to find fullerenes. And actually, in 2010, this group by the Schubilin and collaborators, they produced for the first time a direct transformation of graphene to fulleren. Basically, they have this piece of graphene, and they cut this piece of graphene. Well, I don't know the experimental details, but I understand that with electron beam, they put out some carbon atoms in order to shape a pentagon to promote the bending of the sheet, of the original sheet. And then after this process is continued, in order to have, for instance, 12 pentagons, you are able to find fullerenes. So all this evidence tell us, and also the fact that the electronics degrees of freedom on a sheet of graphene has to do also with the surface, the curved surface, we can ask what are the equations that model the pseudomagnetic, or in that case, what are the field equations that describe the curvature of the sheet of graphene. So if it's possible to pose a theory that, tell us what are the possible structures or carbon structure that you can have putting the ingredients of the graphene. So this is basically the problem statement that for this part of the talk. Basically, this is the work reported in 2024, And basically, we investigate the role played by the Dirac field, thermal fluctuations in the effective spatial geometry in graphene. We provide a shape equation, which is basically these field equations for pseudomagnetic, also for the curvature, for extremal configurations along with the general equilibrium conditions under which they can be achieved. Also based on this naive model for graphene membrane, in the sense that we are considering just Dirac field description, and also we are ignoring for the moment the information of this non-abelian gauge. We discuss the characteristic scale of some of the carbon structures observed in the laboratory, as well as the temperatures at which they should be observed. And also this work is more or less related with this other more formal paper that they ask what spatial geometries do in 2+1 dimensional quantum field theory vacua prefer. So in some sense, they also relate more or less with graphene, and they say that graphene is unstable and the graphene tends to crumple. This is basically related to graphene, what is related. So we wanted to construct a theory in order to understand what are the possible shapes that can have carbon structures, and also what are the conditions needed in order to see structures that have not seen at the moment. So in order to start with the more technical part, let us consider the ingredients of the model. Basically, we are going to consider graphene as a membrane, as a continuum elastic two-dimensional membrane. So it is necessary to do an extrinsic description. So we are considering that the graphene membrane is a continuum sheet which is embedded in the three-dimensional space. And also the descriptions of the electronic degrees of freedom are going to be through a Dirac field defined on a curved space-time. And the space-time that we are considering here is split in this product, basically R cross sigma, which sigma means basically the surface of the graphene membrane. And the reason to take this ultrastatic space-time is because in the case of flat graphene, GAB is just the delta Kronecker, and this is the Minkowski space-time with the appropriate Fermi velocity that is necessary to describe the electronic degrees of freedom in the graphene membrane. Okay, so also one can consider in some analogy, if you want, to quantum electrodynamics, no? Because in quantum electrodynamics, what you have is the classical electrodynamics Lagrangian, which is basically the square of the strain curvature, F squared, and maybe if you want to consider other terms like the topological insulator, like these boundary terms also, you can consider. And here we are going to put a model for the curvature, but now the curvature of the geometry. So one of the questions that we were asked is how much the graphene satisfies the model that we are using, which is based in a model more in the biological context, which is called Helfrich-Kana model. And so in this paper that it was appeared 4 years ago, they employ atomic force microscopy to demonstrate that the bending rigidity of the graphene sheet can be extracted from a quadratic relationship of adhesion energy with monolayer curvatures of roll and unroll graphene. So this is an evidence, an experimental evidence, that the model that we are using, because actually they put in the introduction of this paper, the model that we are using, which is a model that was using in the soft matter context. This is the model. So in some sense, this is like the classical electrodynamics, but now, in analogy, is a model for the shapes of a membrane. Okay, this is a free energy that depends on the configurations of the shape. This X means the embedding function that describes the surface. G represents the determinant of the metric. K is called the twice of the mean curvature. And R is actually the Ricci scalar curvature, which in 2 dimensions, this term is actually a boundary term. So this is exactly as the action electrodynamics that we were hearing from Mauro, because if this Kj, which is the Gaussian modulus, can make position dependent, actually this is not just a constant. By the Gauss-Bonnet theorem, the integral of the Ricci curvature is basically the Euler characteristic plus other terms, well, for compact surfaces, for other terms that depends on the boundary of the surface, no? Like the Gaussian curvature of the boundary and other things. And in the extrinsic description also, there is this relation which was discovered by Gauss and Codazzi that relate the Ricci scalar curvature with the mean curvature and also to the extrinsic curvature. Okay, so in this, the parameters, alpha is the bending energy. This quantity, bending energy, is one of the parameters that was measured in this paper that I was showing. Kg is the Gaussian bending energy, and sigma is a term which is a surface energy, but also can be considered as a constraint to define the area of the membrane. And as was mentioned, there is an experimental support using this Hamiltonian. So now we are going to combine this Hamiltonian that classically, so-called, describe the elasticity of the membrane. So in order to introduce the electronic degrees of freedom, we pose this Dirac field action in the curved space-time, but because we wanted to study the thermal fluctuations of this Dirac field, so we use a finite temperature approach. So we close this part of the manifold and promote the introduction of the temperature. So for instance here, well, this is just the standard spinor, and this is the big transformation that you should do in order to use the finite temperature approach. And this is how this operator turns out when you do this transformation. This operator, this Dirac operator, now, because we have a curve structure, involves also information of the geometry through these Dirac matrices that depends on the local geometry, and also this omega, which is the spin connection, which is associated also to the geometry. Okay, so our hypothesis is that Dirac fields may provoke modifications to the geometry of the membrane through the thermal fluctuations of the fermion gas in the material. So this expression is basically like the effective action in quantum electrodynamics, basically. This is the classical action of the, in this case, of the geometry of the surface, and this is the effective action of the Dirac field. Okay, so this is another relation of this effective action in terms of the partition function of the Dirac fields. And in this term, in this equation phi, also this involves this, the the generation associated to the two valleys. This is GB, and also to the spin. This is GS, and beta is, as usual, the inverse of temperature. Also, here I introduce like a term that G, in order just to tell that the calculation of the partition function will depend on the geometry, okay, functionally. So using more or less the methods that was introduced by Professor Eduardo Fratkin, so you can compute this partition function. You basically, because you have this finite temperature description, you need to introduce a Fourier model composition, and then the partition function can be written in terms of this determinant in the Hilbert space associated to the spinors of this Euclidean Dirac operator. So now we introduce some methods that are very known in the context of quantum field theory in Hilbert space-time. This is one of the best methods in order to see how is the functional dependence on this partition function, which is called the heat kernel. And for instance, through this identity and also this other identity, we are able to write down the logarithm of the partition function in terms of this sum that involves this Matsubara frequency associated to the fermion Dirac field, and also involves this function k, which is called the heat kernel operator. And there are a lot of techniques developed in the past, I would say, in the since DeWitt, the Professor Bryce DeWitt, in order to understand the structure of this function. So we just go back to the books and see how is the structure. And so, for instance, the heat kernel can be written in terms of a sum of O2 curvature invariants. For instance, this is just the identity, a linear in the curvature. This is the Laplace-Beltrami on the curvature, the square of the curvature. But also, we should be careful because this integral also has a pole in this s equal to 0. So we need to isolate the divergence and remove this divergence, introducing these counter terms. And then we have an effective action, which now is renormalized. And this is basically the result, which can be written. This is, I would say, more or less known in the context of quantum field theory. But now it's written in terms of powers of this thermal wavelength. Here appear the temperature and also the Fermi velocity. And these are just numbers that turns out from the renormalization procedure. Now we got our effective model. This is now a new model that is further from the Hellfish Canal model to describe the shapes of the graphene. So this model has several things new. I mean, the Gaussian bending modulus is corrected by the quantum fluctuations, this delta K effective. Also, the surface tension is corrected, but also directly from the Dirac fluctuations appear a completely new term, which is quadratic in the curvature. So the interesting things about these new terms is the fact that, for instance, the correction for the surface tension or the beta multiplied by that is just inverse divided by the square of the thermal wavelength, whereas this new elastic coefficient, I would say non-linear, although all the theory is already non-linear because it's a geometric model, but this is, I would say, more non-linear than these ones, is this coefficient is proportional to the square of the wavelength. That means that, for instance, if this thermal wavelength increase, so this is smaller, but this increase, I mean, this coefficient. So we are going to have different domains of different shapes that can have depending on the value of the temperature. So the natural question here is, what are the surfaces that minimize this effective action, or this effective Hamiltonian? So what are the configurations that, that are expected? Well, naturally, we should recover graphene, or at least the topology of the plane. Carbon nanotubes also is the topology of the plane. Fuller ends, also some hypothetical structures that actually were predicted since 1991 and 1992, which are the carbon Schwarzschites. Carbon nanocones that also have been seen in experiment, carbon nanoribbons. So after a procedure that was developed actually 20 years ago by this professor Jemal Guben, which was actually a professor in this institution, this professor developed these methods in the context of soft matter. We use basically the same methods in order to obtain what are the field equations for the shapes. So these basically are the shape equations. This is the Laplace-Beltrami. This K, recall, is the mean curvature, and this is the Ricci curvature. And the new terms that appear, this term that is here is just coming just from the Helfrich-Canham Hamiltonian, and this one is basically a new term that is coming from quantum fluctuations of the Dirac field. And also in general, as we do in classical or quantum field theory, we can add a source if you want. But of course, I will just present at the moment just a case when j is equal to 0. This purple term that appears here is completely coming from the thermal Dirac fluctuations. Okay, and this is, well, okay. Purple terms emerge totally from the quantum fluctuations of the Dirac field. So now we need to, well, it is, I would say, taking proportions adequately. It's like a, well, this is just an analogy. It's like the general relativity field equations, but now are the, I would say, the field equations for the shapes of the carbon, taking into account this hypothesis. So, which we look at simple elemental solutions. For instance, if we take r equal to 0, this corresponds to the topology of the plane, and k equal to constants inverse of this radius. This basically defines a cylindrical surface. We can put this information into the field equations, and we arrive to this equation. So this means that this sigma effective, which is the surface tension corrected with the quantum fluctuations, should be positive in order that this has sense. And also another solution is the spherical surface that satisfies the shape equation. I mean, you are able to see that for the spherical surface, the square of the mean curvature is twice of the Ricci curvature, and k also is twice one of the radius of the sphere. And also, we arrive to this, but these coefficients, if you remember from above, is negative here. Is negative. So this means that in order to have this configuration, at least as a solution of the field equations, we need that this sigma effective is negative, should be negative. So this means that these conditions for the cylinder or the sphere impose an upper bound and a lower bound on the equilibrium temperatures in order to have these cylindrical and spherical configurations. By the way, one can write down the structure of this critical temperature in terms of this sigma parameter completely. So we can characterize, if we have an experiment where we compute this value, we can determine in principle the value of the critical temperature. So when we play with the solution and we write down the mean curvature and the Ricci curvature in terms of the temperature, we're able to write down this structure, which seems to me as a structure that appears typically in phase transitions. So for instance, for the mean curvature, we have this structure for the mean curvature in terms of the temperature, which is valid just for T less than critical temperature, while for the sphere, the temperature should be bigger than the critical temperature. This means simply from the solutions that we are not able for a temperature synthesis to produce, for instance, carbon nanotube and fullerenes in the same phase or in the same temperature, I would say. So also we can have more solutions related to the configurations, the carbon configurations that we mentioned in the beginning. More solutions are minimal surface, minimal surfaces and developable surfaces. So the contrast between the effective coefficients that I was mentioned before, that this is just 1 over the square of the thermal wavelength, and this is proportional to the square of the thermal wavelength. So these define high and low temperature regimes. So we can investigate how is the shape equation, how the shape equation reduces in the case when temperature is much more bigger than the critical temperature, and in the other way, when the temperature is much more less than the critical temperatures. So what we got is that in the first case, when the temperature is much more bigger than the critical temperature, we got this K equal to 0, and in the other one, this more horrible equation, but has a solution, a simple solution, which is R equal to 0. Well, it turns out that in the second case, R equal to 0 is not just simply flat. It's what it's called developable surface. Basically, it's a surface that you can find with, for instance, a sheet of a bond sheet, and you can just bend, and this will have a curvature, a Ricci curvature equal to 0. So basically, this is characterized because of the fact that you have a straight line, and this straight line is swept in the space, and the surface that you got is basically a developable surface. Also, cylinder is a developable surface, but graphene is a developable surface, etc. And also this twisted nano ribbon. In the other side, in the high temperature regime, we got this K equal to 0, and this is actually a big field in mathematics, which is called the investigation of the minimal surface that satisfies that the mean curvature is equal to 0. One of example of this mean curvature is this one. And this recall actually the proposal by Umberto Terrones and McKay in the 1991 for the Schwarzschild structures. These are characterized because of the local of the, if you take a local patch, this looks like a monkey saddle surface. Okay, so, but how stable are the configurations mentioned above? I mean, if we wanted to have a phase diagram, we need to study the stability analysis. So in this case, because it's just a mechanical stability analysis, we just take the second variation of the Hamiltonian. And this is, for instance, the second variation can be expressed always in terms of this functional term that involve this operator, LF, and this phi is a scalar field, which is the deformation of the surface along the normal direction. So for instance, this operator is a differential operator that for this contribution of the effective Lagrangian has all these structures. So we need to substitute here the expression for the cylinder, for the sphere, for the developable, for the minimal surface, and to see what is the spectrum of this operator and also the other operators that appear from the effective Hamiltonian. So after the analysis of the spectra of the full operator, so we are able to show that there is an stability region for the carbon nanotubes. Basically, there is this condition for the temperature, that this means basically that the temperature for the carbon nanotube synthesis are stable, these structures, just between these two values of the temperature, the critical value and a minimal value of the temperature. Also for fullerenes have this value. For minimal surface, just we need to consider alpha bigger than 0, the bending parameter, and but for much more higher values of temperature in comparison with the critical temperature, these structures are unstable. And the developable surface are unstable for all the region. These quantities C and D that appear in the equations are depend on the parameters of the model. So using the experimental measure value doing by the 5 minutes or 10 minutes? 5 minutes, okay. Doing by the guys that prove that the Hellfish-Canham Hamiltonian is adequate to describe the elasticity of graphene. Taking this value and you see the values of the radii of the carbon nanotube and the fullerenes, and also some characteristic synthesis temperatures, so we are able to find some bounds or at least some values for the critical value and the minimum value for the carbon nanotubes. And actually, also, we are able to show that the maximum temperature where the fullerenes are stable is much more bigger than the critical temperature. So practically, once when the fullerenes are synthesized, they are stable. And this is the phase diagram. So this is the mean curvature, also the Ricci curvature, against the ratio between the temperature with the critical temperature. Also, we can write down some phase diagram for the free energy in order to see that the discontinuity here that reveals a first order phase transition. And this region is just the region where the carbon nanotubes are stable. As I mentioned, the fullerenes are practically stable in all the region. For temperature much more bigger than the critical temperature, we got the minimal surface. These are other examples of minimal surface. De hecho, in fact, there are an infinite minimal surface that you can construct. So there is a lot of, there is a plenty in the room to play here with these surfaces. In the other side, I just put some examples of developable surface, the nanocone, these nano ribbons, and the graphene, which actually in our analysis implies that graphene is unstable and because of the thermal fluctuations and tends to crumple, as was also observed in the other studies. Okay, now I think I cannot go in that direction. How much time do I have? 4 minutes. This is the quantum topology, which maybe is the most interesting part for you, but because you know already this, in these 4 minutes, I would say, I just wanted to pose that I would like to have the perspective by Duncan Haldane and Shankar to see well, maybe it's the same perspective more than this, just two guys, to see the physical space as a geometrical space. So the Hilbert space actually is not just this vector space, it's actually this projective Hilbert space. So you can build this projective space as a complex manifold, actually. So we can use a lot of information of the complex manifolds or complex geometry in order to analyze. So my perspective is to use Bargman invariants in order to describe, for instance, the probability in quantum mechanics, and also you can define an Bargman invariant, which is invariant on the local U1 terms. And using the Bargman invariants, you can able to define a measure, a metric, in the space of the projective Hilbert space. And with this metric, for instance, if you take 2 points in this manifold of the space very close, so you can define what is called, and it has been mentioned here too much, the Pacharatman-Berry metric. But now, for me, it's very nice to write down in terms of these projectors. This actually you can able to write down in terms of the Fubini-Studi metric, and also using the third Bargman invariant, you are able to write down the Pacharatman-Berry curvature, also in terms of the projectors. Now, for instance, in tie-binding systems, basically the space of states is this manifold in general for n levels. Usually, for instance, for graphene or for the Haldane model, is just CP2, which is actually isomorphic to the sphere, which is the complex projective space, and these are the space, the state of space. So, for instance, for the Haldane model, I think this is very well known for you. You using these quantum geometry formalisms, you are able to write down, for instance, the Hall conductivity, write down this phase diagram that was published in the Haldane paper, original paper, but also you can characterize the phase diagram using the phases of this system using the Berry curvature. So you can write down the Berry curvature. For instance, you can see that there are the same number of peaks pointing just in that direction and also in the down direction. And this means that you have an unchurned insulator, because basically the integration, the volume behind the surface will be zero. And so you can use somehow the Fermi curvature as a, I would say with points as an order parameter, but in the space of states, in order to characterize the phase transition. So for instance, in this point that you have these values, if you substitute in the Hall conductivity, you have this Berry curvature, but if you integrate, you can see these maximums and minimums, and you are able to prove that the integration is actually zero. And this is consistent with this. Well, this is already when you have in the topological phase, all the peaks are pointing in that direction, just in one direction. And in this case, the integration of the Berry curvature. So now just 2 slides now. This is just work in progress. So this is the model that I have been used in order to study these topological defects, including the non-abelian gauge through this SU2 color doublet, which actually are pure gauge, but the integration of this F is not zero, because somehow you can interpret these heptagonal incisions like there is a monopole inside of the material that produce, so there should be a line of discontinuity. So using the quantum geometry formalisms, in principle, you can compute this quantity, or at least to see what are the equations for this quantity using the Dirac equation in curved space coupled to this non-abelian gauge in order to compute the Berry curvature. So we expect that FAB capture information of the actual topological defects on the lattice. So I would say I will put here, and thank you very much.
Questions?
I would like to ask briefly about the motivation, if you wish, maybe, and validity range of using this method of integrating out fermions to get the geometrical corrections. Generically, when the excitations are gapless, integrating them out is not really well defined because essentially they are affecting infrared physics. And also when you change the topology and, for example, end up with compact objects like fullerenes, then the spectrum of the excitations will be gapped, those fermions, because of the compact geometry and finite size. So I'm wondering if you are deriving them without making those assumptions, and then there should be some sort of validity cross verifications at the end, right?
Well, I think I'm not sure if I understand exactly the question, but well, this is the integration of the Fermi, the Dirac field, which is very standard, and
but it's a free Hamiltonian with zero gap.
Yes, that's all right. It's a free
But at the end, it may be inconsistent with the final geometry that you obtain when compactifying the surface.
Yes, yes. I mean, we have not included this contribution. I mean, this gap.
Okay.
It's just the Dirac model, and just we integrate out the Fermi.
Thank you.
Thank you for this very detailed and interesting talk. So actually, my question is about this as well. So you have the metric appearing here for the Dirac action,
Here.
but there is no spinor connection. Is that right?
No, there is a spinor connection. It's actually here.
Oh, okay. So
Because-
that's included.
It's included here in this Euclidean Dirac operator. It is included. Yes.
Okay, thank you.
Yes. Actually, I would like to mention that, for instance, when you have just a strictly 1+1 system, like the mention in the talks, you don't need to include the spin connection in that case. But this is somehow 1+2 dimension.
Another question or comment? Well, I have a question at the beginning. You put this geometric, this surface, this graphene surface, but I don't see where you put explicitly that you have this lattice, that is graphene lattice, in the deduction that you have.
Well,
Because you say until the end you arrive at an expression and say, now I can put the nanotubes or the graphene. So then it's in general. Then you are using a general formalism, describing a surface and finding the Hamiltonian.
yes, definitely. Well, the main thing where information of the graphene, of the lattice, I would say, is in the Dirac description. It is known that the graphene, usually you can model using the tie binding model. This is the standard description. But when you go to the low energy regime,
No, but in the first part, you in the classical part that you mentioned.
well, in the
classical part,
this part,
yes,
well, it is just a membrane, no?
just a membrane.
It's just a membrane, but it is supported with this experiment, no?
Okay.
In this experiment is using a real graphene, and they are using
I
this
understand.
atomic force microscopy to.
I understand. Well, you have.
So just a very small comment. So I think that, so the formalism is expressed on a continuum, but to make the point on the connection to the Fullerene, you want to think in terms of plaquettes, because you have, a pseudospinor per unit cell, and so on the Fullerene you have basically only 30, unit cells, so to say. And so that's where that continuum description kind of is inconsistent with the number of spinors that you have due to the system size.
No, that's right. I mean, strictly speaking, all the materials are discrete, no? But in fact, there are papers, for instance, by Maria Bosmediano in the past, in the 90s, where they describe the energetics of fullerenes using, a very well justified Dirac equation that include this non-abelian gauge in order to describe the spectrum. At least this spectrum is very well compared in the low energy regime. So that means that something happened still in this finite number of atom structure, that there is a field, well, this is my conception, that there is really a Dirac field even if we see this microscopic structure, which is around the sphere, because this is the topology of the Fullerene. But just valid in the low energy regime. This is just
Well, we thank again to the speaker.
Thank you very much.
And please, there is an announcement that there are posters outside. Please, you can go there.